The mathematical fiction genre, it's not a very large section of the library. There's some bestsellers, but they're really few and far between. Tops is definitely Alice's Adventures in Wonderland by the mathematician Charles Dodson, aka Lewis Carroll. Now, in 1884, 20 years after Alice, London schoolteacher Edwin Abbott published Flatland, A Romance of Many Dimensions. In this book, he was critiquing Victorian England and social hierarchy, but it was also a metaphor for understanding four dimensions and higher dimensions. It wasn't actually widely read until Einstein's work on space-time as a four-dimensional construct. That was general relativity in the 1920s. And that's when this book became a lot more popular. It's a story about shapes living in a two-dimensional flat land, a flat world. They're living in a surface, and that's very different. They can't see outside that surface at all. When they meet another shape, they can't see around. They can't see inside that shape, only an edge. There's no real realization that a third dimension exists. If a sphere were to pass through this flatland, they would see it first as just a dot, and then a short curved line, and then a growing line, but then finally shorter again to a dot and gone, and the sphere passes out the bottom. But of course, we only think of it as the bottom because we're in three dimensions. These creatures in two dimensions have no understanding of that third dimension. And that's the analogy to how we three-dimensional creatures perceive four dimensions. Abbott was saying to understand four dimensions, we have to understand first how three-dimensional objects look in two dimensions. And we're going to look into some of that weirdness and some of the strangeness that's possible in two-dimensional and three-dimensional space. Some of those weirdnesses only live when you're actually in four dimensions. So let's go back to the Möbius strip, back to two dimensions. It's locally two dimensions. Because of this twist, if we take a strip of paper, we can't embed the Möbius strip in two-dimensional space. If we have a strip of paper, you could think about bending the tops around when we make just a regular cylinder. But in order to do the twisting happens to happen. We have to bend out of that plane in order to get the twist. Now, there's two characteristics we know about Möbius strips. One is that it's non-orientable, and the other is that it's one-sided. The non-orientable means that your left and your right can switch if you go around it. The one-sidedness means that if you're crawling along it and you keep crawling, you'll end up on the other side, so there's really only one side. So this idea, this orientable, is really important in topology, right? Imagine that you're living in the surface and not on the surface, sort of like Abbott's two-dimensional creatures. If you're in the surface, you're a two-dimensional object, and say your right hand is red, and you walk along and you pass some cute little black line on your right. If you go around the strip and you come back on the other side, remember, we're not on the surface, we're in the surface. If we come back around the other side, it's no longer on your right, it's now on your left, right? So your left and your right switched. That's the idea of non-orientability. If you're on an orientable surface, your left and your right never switch. These are the surfaces we know well. A sphere, a cylinder, all of these things are orientable surfaces. If you're on a non-orientable surface, sometimes your left and your right switch. Now, because this Möbius strip is the most common thing that we know of that's one-sided, and it's the most common thing we know of that's non-orientable, you might think that non-orientability and one-sidedness are really the same thing. One goal of this lecture is to convince you that they are different. You see, orientability is an intrinsic property of a surface. It's about living in the surface, whereas sidedness is an extrinsic property. You have to think about living on the surface in order to talk about the sidedness. We're going to show you a really strange object. It's a Möbius strip, which we sort of always know. Every Möbius strip you and I have ever played with has one edge and one side. We're going to show you one which is non-orientable as usual, and it just has one edge as usual, but it's two-sided. There are a lot of mathematicians who don't know that such a thing exists. it'll take some work to get to that, so stay tuned and make sure you're paying attention. To understand a really mind-bending three-dimensional space, let's think back to a two-dimensional torus. So we start with a square, and we're going to glue opposite edges together. The strangeness of life on a torus, or maybe in the surface of a torus, looks like this. If you're living in a torus, if you look sort of forward, that you would look around to the opposite side, and so you would see your own back. If you looked past that again, you would see another copy of you, and another, and another. You know, it's only curved if you're thinking of it from a three-dimensional perspective. As a two-dimensional object, your space would feel flat to you. And the same thing works if you look to the left or your right. If you look to the left, that light would bend around and you would see your right side. And if you look past that, you would see it again. And I want to be clear, this wouldn't be sort of a mirror illusion. This would be actually you. You would see you again. You know, one way to think about this would be to think about living on the Earth and looking all the way around if the light bent around and you could see your back. So what would a higher dimensional version of this look like, where instead of a square or a rectangle, we started with a cube? That would be a pretty strange space. Let's see what it would look like to live in a space like that. A three-torus is an example of a three-manifold. It's one of three we're going to explore today. And by three-manifold, I mean a smooth space that looks locally like this. It has three dimensions. So let's start in this cube. And we want to glue opposite sides together, left to right, top to bottom, and front to back. We can't do this in three dimensions. There's not enough space in some sense. But with video tricks, we can visualize exactly what's going on in this space. Let's do the left-right gluing first. See, if we connect the left to the right, let's do it with no twist first. So if we had enough space, it would sort of come around and glue sort of like this. Now, if I'm in the space and I walk out on your right side of the screen, what happens? I come back in on the other side. My watch, it's still on my left wrist. And that's because the three-torus is orientable. This orientation is fixed. It never switches in this space. It's a good thought question. When the left and right sides glued, what do I see when I look this way? Hey, look. It's my head, the back of my head. And there's a me in front of it, and I'm pointing. It's like being on a small version of the Earth, and you look forward and you see yourself again and again. What happens if I have a ball to throw? I can play catch with myself, and the ball will just come back the other side. Let's watch. I can go back the other way, too. Nice throw. Nice catch. And now that we have this left-right walls glued, we can also glue front to back. And when we do that, it looks like a room of mirrors, sort of, right? Except that it's not. If it were a mirror behind me, you'd see my back, but you see my front. And remember that there's just one of me. It's just the light going around and around and around. You think this is me? So is this. You know, on a two-torus, you walk around either the short way or the long way, and you come back to the start. Here, you walk left, and you come around from the right. Oh, and you can do that front to back as well. I can play catch with myself this way, too. I can throw front to back. Remember, there's just one of me. You just see it infinitely many times. If I threw this ball really hard, you'd see it go by again and again and again before it actually hit the ground, because we're not in a very large three-torus. Now, if we connect the top and the bottom, things get really trippy very quickly. You'd see a layer of me's above and below this layer. Again, it's still just one me. I could play catch up, down. I could play catch diagonally. With the two-torus, you go around the short way or the long way. With the three-torus, you can go left, right, front, back, or up, down. That's really mind-bending. But let's visit a three-manifold that's even crazier. All right, we'll start back in a regular space, a cube. And remember the Möbius strip where we took a strip and we glued the ends, but we gave it a twist? Let's do a three-dimensional version of that. What happens if we twist the cube before we glue? We take the original cube, we glue left to right, but we twist first. Things on the left and the right will switch. Now, watch closely. My watch is on my left hand, and you see the flag like this. Now, I come back in, and from my perspective, my watch is still on my left hand, but you probably disagree, and you probably think the flag is switched back as well. I read left to right, no problem. But when I do this, it probably appears that I'm reading right to left, because you didn't make that switch. Let's go back. Life in this space is a little bit weird. I come back again, and I should look normal to you again. Now, let's make sure we understand this space. So, let's suppose I have a sign. So it says great courses. I put my initials on the front, but on the back, there's no initials. Now, what happens if I hold it out here, out to the edge of this space? Look, the sign comes in, but if you look closely, there's initials on that. That's pretty weird. All right, let's get rid of the sign. Let's take a strip of cloth and extend it all the way across this room. And when it gets to the edges, remember that it's attached on both sides. But remember that there's a twist. And so the back edge of this side is attached to the front edge of that side. The back edge over here is attached to that side. And that means it has just one edge. The back is attached to the front, which is attached to the back. It's a Möbius strip. Now, most people think a Möbius strip has one edge, that's correct, and one side. That's usually correct. What we have here is a Möbius strip with one edge but two sides. It's a two-sided Möbius strip. You see, an ant crawling on this strip would crawl out that side on top and come back on top. It's left-right switched, but it's still on top. An ant on the bottom would crawl out and stay on the bottom. The two ants would never meet. This Möbius strip, it has two sides, a top and a bottom, and that's different from every Möbius strip you've ever seen and you will ever play with. Me too. Now, it is still non-orientable. If you think about living in the strip, if you walk out that side, you would come back from this side left-right switched. That's non-orientable, like regular Möbius strips. The non-orientable aspect of this Möbius strip, it isn't in the strip itself, it's in the ambient space. And that shows us a really important distinction. Orientability is intrinsic to the space. We have to be in the strip. Sidedness, the number of sides, it's extrinsic to the space. You have to think outside the strip. We have one last mind-bending three-manifold to show you. Let's start back in the space again, a basic space with a cube. We're going to glue the left side to the right side, but instead of doing a flip, let's do a quarter turn. Think what happens. If I walk out that way, I would come back in this way with my head pointed toward you. If I do it again, well, let's just see. Oh, you're up there. That's funny. I'll go around one more time. Oh, look, you're upside down. Gravity must be really peculiar in this space. Let's go one more time around. Oh, hi down there. Why do we care about this? Let me flip around and tell you. Let me give you 3 reasons we want to think about spaces like this. First of all, it's fun to bend our minds in these ways. But second, there's really beautiful art that's based on these ideas. Jim Milner's work is particularly gorgeous. It plays on these ideas, but stays just in 3 dimensions. It's stunningly beautiful lines and paradoxical properties. This one has just one face and one edge. But third, and most importantly, our universe might be like this. Let me explain. We don't know what the shape of our universe is, in the same way that 4,000 or 5,000 years ago, people didn't know the shape of the Earth. If we go far enough in one direction in our universe, would we come back from the other direction? Would we be flipped or flipped? The universe is so large that light hasn't made it that far yet, but these are legitimate scientific questions. There are experiments designed to measure the shape of space. All right, so these spaces are really twisted, but you don't have to go to the edge of the universe to see some of the twistedness of topology. The quick conundrum. Here's an amazing topology demo we do with our students. Derek here is going to help me out. This t-shirt is a little strange. It says outside on the outside, but on the inside it also says inside. It's clearly marked. Now, it would be easy enough for Derek to take this shirt off, turn it inside out, and put it back on. The trick is, can we do that when his hands are clasped? And can we do it without him letting go of his hands? So let's see if we can do this. Well, we take this up and over his shoulders and off his head. And now here is the tricky part. We have to pass the entire shirt through one of the armholes. So we get the entire shirt goes through the armhole, and it comes out the other side. And now we can see we sort of have this. Now we can put it back over. Now, I think there's space for your head, Derek. Look, there's a place for your head. You haven't let go of your arms, I hope.
Nope.
Okay. And now we get it over your shoulders, and look. We've managed to turn the shirt inside out without ever dropping his hands. It's a great demonstration. What we're actually doing is we're everting the torus. An eversion is turning something inside out. And it's really a torus. If you think of extending these sleeves all the way down, it's really a torus that has a hole in it. Now, you can do an alternative version of this. You can tie your feet together with a rope, and you can turn your pants inside out with going over the rope. That one's a little bit trickier. Leonhard Euler was an 18th century Swiss mathematician. He found an unexpected way to distinguish spaces topologically. It's a really non-trivial problem. Imagine that you're living on a planet. How could you determine, just from sort of your local space, the topology of the planet? Is it a sphere? Is it a torus? Are you living in a really strange projective plane? Maybe all you have are sort of flat maps, but you have flat maps for all of the areas. Could you use math to tell you the topology of your surface? It turns out you can, and it's called Euler's characteristic. We usually use the Greek letter chi to signify the characteristic. If you live on a 2D boundary surface with no boundary, you calculate chi just from these maps, and it can tell you the topology of the surface. And it turns out it's not hard to calculate. Let's look at a quick example. Say you're on a sphere, and you draw any set of dots and connect them with lines, no crossing. You would create countries. And now let's talk about those countries. Let's just think of those as faces on your sphere. We could count the number of faces, but we could also count the number of edges from one vertex to another. That's an edge. We could count the number of edges. We could also count the number of vertices where two or more edges meet. In this case, chi is going to be the number of faces minus the edges plus the vertices. You keep going down in dimension, faces, edges, vertices, and you alternate the sign. Here's the amazing thing. No matter how you draw this map on a sphere, if you take the faces minus the edges plus the vertices, you will get 2. Always, every time. We can check with some of the Platonic solids that we know. Every time, all of these are spheres topologically. We could sort of morph them and get spheres. When we look at the faces minus the edges plus the vertices, we always get 2. Let's just take one, the dodecahedron. Dodecahedron has 12 faces, 30 edges, 20 vertices. 12 minus 30 plus 20, we get 2. All the others work out as well. How about a torus? Like, what if you drew countries on a torus and then did the same thing? Well, on a torus, if you take the faces minus the edges plus the vertices, you always get 0, no matter how you draw those. Take a 2-hole torus, like the teapot that we have back here. You take a 2-hole torus and you make countries on there, faces minus edges plus vertices, you always get -2. Every time you glue on another torus and sort of smooth out the edges where you just glued it, chi goes down by 2. You have a sphere at 2, a torus at 0, a 2-hole torus at -2. It just keeps going. What about projective planes? You could try to picture a projective plane, with a rectangle with glued edges, and you could draw countries and count them. And the answer when you do that, you would get that the faces minus the edges plus the vertices is always 1, no matter how you draw those. When you connect a couple of projective planes together, it's already hard enough to picture one plane. Picturing 2 coming together, that's incredibly hard. But turns out you get a Klein bottle if you do 2 of those. And every time you add another projective plane, if you stitch it together, chi goes down by 1. Amazingly, all these surfaces without a boundary, where they're not going off to infinity, all of them are either a sphere, a bunch of tori stuck together, or a bunch of projective planes stuck together. It's called the classification of closed surfaces. This Euler characteristic gives us an interesting question. So chi of the torus is 0, and chi of the projected plane stitched together with another projected plane is also 0, and the chi of the Klein bottle is 0. Maybe those three things are actually topologically equivalent. Now, it turns out no. See, the torus is orientable. You never switch your left and your right. So those are not all the same topologically. But how about a torus stitched together with a projective plane? See, the chi for that is -1. And if you took 3 projective planes, you would also get chi of -1. And both of those are non-orientable. Are they topologically equivalent? It turns out they are. It's really hard to picture that. If you tell me the orientability and the Euler characteristic, the info, and the Euler characteristic you can get from just a bunch of maps. You just count the number of faces on these maps, the edges and the vertices. If you give me that information, orientability and the Euler characteristic, I can tell you what surface you're on. Just from maps, flat maps of local areas, you can figure out what kind of surface your entire space is. So why is it that the Euler characteristic is like this? I mean, why doesn't it matter how you draw the countries, the borders, the vertices? To answer that, we actually go back to the different geometries we talked about earlier: flat geometry, elliptic geometry, and hyperbolic geometry. And one of the things we need is a key and strange fact about triangles in these different geometries. You probably remember from high school geometry that in a planar world, in a flat world, every triangle has the sum of the vertices is 180 degrees. Let's measure those in the normal measurements we use in mathematics. We'll use radians. It's pi radians. Now, if you have a spherical triangle, we're using for edges the great circles. If we intersect great circles, we could come up with a spherical triangle. And it turns out that the sum of the angles in a spherical triangle is always greater than 180 degrees. Even stranger than that, on a unit sphere, the area of the triangle is precisely determined by the sum of the angles. The area of a triangle on a unit sphere, it's the sum of the angles minus pi. It makes a little bit of sense. You see, small triangles have small area, right? They're flat, and the sum of their angles, if they're flat, the sum of those angles is really close to pi. On the other hand, you could imagine expanding and getting like 1/8 of a sphere. If you had 1/8 of a sphere, then all 3 of those angles are exactly right angles. The sum of the angles is then 3 pi over 2. The sum minus pi is pi over 2. So this formula is saying that the area should be pi over 2. And that checks out because you have 1/8 of a sphere. The surface area of a sphere is 4 pi. 1/8 of that is pi over 2. So this sort of does make sense. Hyperbolic triangles are also interesting, and they work sort of in the reverse way. In that case, the sum of the angles is always less than 180 degrees. And the area in this case, if you're working in some sort of unit hyperbolic space, it's pi minus the sum of the angles. So you can actually see that in something like this. See, the smaller triangle here, what you have is that the area is pretty much like a flat triangle. But as you get bigger, look at the angles. The angles are getting smaller. The bigger the triangle, the smaller the angles. And that's what this formula is telling you. It's not too hard to prove, but there's so many more mind-bending topics that we need to talk about. In particular, I want to talk about how 2 things are connected. You see, geometry seems really rigid. It's fixed. Scaling matters. The size of things matters. We measure things in geometry. Topology feels like the sort of loose, rubbery, morphing doesn't matter sort of thing. But amazingly, they're connected in an incredibly deep way. Now, many proofs of the Euler characteristic, this is something from topology, they use very advanced mathematics. Here we're using geometry to prove it. Here's a simple case to give you an idea. On a unit sphere, all countries are, say, triangles. So let's just assume all countries are triangles and all edges are straight. And the goal is to prove that the faces minus the edges plus the vertices is equal to 2 on any sphere. So let's do some quick calculations. So let's say you have n triangular countries. So the number of faces is n. Let's look at the edges. If every country is a triangle, then if n is the number of countries, then you should have 3n edges, except that every edge is shared by 2 different faces, 2 different countries, and so we have to divide by 2. So the number of edges is then 3n divided by 2. Now, the vertices, it turns out, they're not as easily related to n. And so let's just solve for the vertices. So the vertices, if we wanted to reach our goal, the vertices should be equal to 2 plus the edges minus the faces. We figured out those. The edges were 3 over 2 times n, and the faces were just n. We simplify, and we get our new goal. We're trying to prove that the vertices are equal to 2 plus n over 2. And that's where we use geometry. You see, for triangles on a unit sphere, the area of each triangle is the sum of the interior angles minus pi. We know the surface area of the entire sphere. The surface area of the whole sphere is 4 pi. And so 4 pi should be the sum of all of the areas of all n triangles. Now, each one of those, each triangle, has an area which is the angle sum minus pi. So what we really want to add up, to get 4 pi, we should add up all of the angles in all of the triangles minus pi. We take each triangle, the sum of the angles minus pi, and then add all of those numbers up. Well, that's the sum of all angles over the entire sphere minus n times pi, because there were n triangles. And now, the sum of all angles, every time we have a vertex, we're adding up all of the angles around it. When we add up the angles around any vertex, we should get 360 degrees, 2 pi. And we have v vertices around the whole sphere. And so the sum of all of the angles should be v times 2 pi, and we have to subtract off n times pi. Well, we can simplify that. We factor out 2 pi, and we get v minus n over 2. And now we can solve for v, and v is equal to 2 plus n over 2. We got it. And that implies our original goal, which is that the faces minus the edges plus the vertices is equal to 2, no matter how many triangles you have, no matter how you draw them on the sphere. See, that was using geometry. So we had this fixed sphere, we were using the geometry of it. But now that we've proved this, you can morph this, and you still have the same formula, that the vertices minus the edges plus the faces is equal to 2. When you morph something like that, you're not changing any one of those 3 numbers. In the general case, you would have to do non-triangles. And so first you do it with triangles, and then you think about removing an edge. Now, if you remove an edge, the vertices stays the same. We haven't changed that. We've removed one edge, so the edges goes down 1. And the faces also goes down 1 because you're joining 2 adjacent faces. So you remove as many edges as faces, and so the formula doesn't change. Now, if you're working on non-spheres, it gets a little bit trickier. It's something that's really good for you to work on. But the result that you get is that for a hyperbolic space, the area is going to be equal to negative 2 pi times vertices minus edges plus faces. And that's negative 2 pi times chi, the characteristic. In a flat space, 0 is equal to 2 pi times the vertices minus the edges plus the faces. That's 2 pi times chi. And in general, you get an interesting formula. You get kappa times area is equal to 2 pi times chi. Kappa here we're using for some sort of idea of curvature. It's +1 for spherical spaces, 0 for flat, and -1 for hyperbolic spaces. And that leads to something even deeper, which is the Gauss-Bonnet theorem. So if we use kappa as a measurement of the curvature, where kappa is 0 for a flat space, and it's positive for a spherical space, and it's negative for a hyperbolic space, like the Pringles chip or the crocheted space we have over here, the general Gauss-Bonnet theorem does something like adding up the curvature over the entire surface using an integral. And the result when you add up the curvature over the entire surface, it's 2 pi times chi, the Euler characteristic. That's really amazing. You see, the left side of this equation, the integral of kappa over the entire area, that's a measure of how curved the surface is, and then you add up that curvature over all of these places. The right side is 2 pi times chi, the Euler characteristic, which is vertices minus edges plus faces. It doesn't matter what the map is, what the countries are, what borders you draw on. To say this another way, the left side is geometrical, where scale matters. We're measuring curvature and adding it up. The right side is entirely topological. Take a surface, bend it, twist it, stretch it, it doesn't matter. If you bend and twist and stretch it, it won't change the topological properties, but it definitely changes the curvature. It changes the geometry. But apparently, according to this formula, it doesn't change the sum of the curvature over the entire surface. Somehow the topological information, the number of holes, whether it's orientable, things like that, it's encoded not in the curvature at any one point, but in the sum of the curvatures over the entire surface. If you enjoyed this foray into the strange world of topology, I encourage you to grab Jeffrey Weeks's The Shape of Space. The math world is deeply indebted to Weeks, who took a really impenetrable topic of three manifolds and explained it to non-experts. Next time we turn to something else, we turn to doing the most with the least, looking at geometrical optimization.